Thomas Nowak. I am currently working as Vice President, Government Relations and Public Affairs for a Swedish scale-up called Qvantum. We have nothing to do with quantum computing, but we are building heat pump systems. We could cool quantum computing centers easily and would gladly take the waste heat that they produce. Previously, I have been the Secretary General of the European Heat Pump Association, and in that role I have participated in quite a few projects, and I have also established the Large Heat Pump Working Group, and some of the project partners are also part of that group in the association. So I'm very delighted to see that heat pumps have made it out of the small area of residential applications into industrial, and that we can show big kit to policymakers and other interested stakeholders. In my opinion, and not only my opinion, in the opinion of many experts, heat pumps are the most efficient technology that we have. It's certainly the most efficient when it comes to providing heating and cooling, and they are second to none. If you can combine heating and cooling at the same time, if you demand heating and cooling at the same time, then of course you can reach outstanding efficiencies. And a typical heat pump has probably an efficiency, 1 unit of electricity converted into 4 units of heat. If you typically do that, if you add cooling to that, then you can go up to 1 unit of electricity, giving you 7, maybe even 9 units of heating and cooling combined. So you have a super big outcome from the investment of 1 unit of electricity. And then we do need ambient energy or geothermal or waste heat as fundamental energy source that is then upgraded by the heat pump. And we can do this. We can use waste energy from cooling, and by doing so, we can close energy cycles. So I like to say that what we should aim for is a closed energy economy instead of only a circular material economy. We should also have a circular energy economy, because then we can reduce the final energy needs of the society by a tremendous amount. If we base the answer on the question on the statement that the technology in principle is ready, then we do indeed need policy innovation and we need social innovation. It could start by a full recognition of the benefits of the technology, including for industrial processes. What we do need is all policymakers understanding it that way. And then, of course, there are some market factors that have an influence. And one is how cheap is the incumbent technology, how cheap it is to operate a fossil combustion process versus a heat pump. And quite often it is, at least in the short-term perspective, cheaper. And industrial processes are often calculated with a very short expectation to the payback period. So that needs to change. It can be changed if electricity, the ratio between electricity and gas prices are significantly reduced. I think a value of 2 about is correct, because then you would be able to compensate for the higher initial investment over the lifetime of the project. For the time being, it seems also relevant and important to still have some subsidies for the initial investments to get the whole engine moving of this transition of the energy system. And then we need to make everybody aware that the technologies that exist, and that's not only the general public or the decision makers in industry, it's also the professors, the universities, the research institutes, so that we also have an inflow of talent into the sector. For sure, if we have a more mass production approach, that would help. At the moment, we are building pretty much every heat pump custom made. So you look at the process, then you go back to the drawing board, then you come up with a test bed, then you test it, then maybe you optimize it, and then it's installed. That is not feasible if you want to decarbonize parts of industry. And mind you that in Europe, the industrial heat demand of below 200 degrees is around 2,000, industrial heat demand is around 2,000 terawatt hours. And depending on the study you're looking at, it's between 35 and 40% of that is in a temperature range up to 200 degrees. So we have a huge amount of energy that we can replace, that we can move from fossil energy input to renewables. So obviously that also means megawatts and gigawatts of installed capacity, and for that we need new players in the market, but we also need the old players to increase their manufacturing capacity. So more standards, more standardized heat pumps would help. At EHPA at that time, we have done one project with the paper industry where the clear target was to build a standardized kit, a standardized solution for paper mills. And the result was a two-stage process with a small heat pump that would bring us a low-pressure steam at 120 degrees, and then a vapor recompression machine that would then bring it up to 180, maybe 200 degrees. So there's already the idea to say, let's take vapor, low-pressure heat pumps, which are now increasingly becoming standard, and let's take quite standardized and quite common vapor recompression technology, merge the two together, and then we have a solution that can be operating at scale. And it can also scale better to the industrial demands because the vapor recompression is a bit more flexible than the heat pump. The project design shows that it's a good idea to use many energy sources at a lower level. In this context, of course, lower level is not what you and me would consider a lower level, right? I mean, we're talking 80, 100 degrees. So for many people, that would be a high temperature. But in the industrial context, of course, it's at the low end of the spectrum. But if we can use waste heat sources at this level and upgrade them to 200 or 250 degrees, that would, of course, be very beneficial because it extends the envelope at which heat pumps can operate. I would say that today the 160, 180 degrees is roughly where we can say, okay, we have reliable solutions. And if that can be extended at efficiency, because that's the big key word, it can be done today. You can go to 250 degrees, but you will not be very efficient. So if the result of this project makes this temperature level achievable at higher efficiencies, then of course it will make the usefulness of heat pumps available for many more industrial sectors. Let's start with that first. That's an interesting question because then we would have to answer what means artificial intelligence in making such a process more efficient. What would that really mean? I would be very interested in learning more about that. What you typically understand is to use sensor data and then be able to match supply and demand, maybe even integrate electricity at low prices and avoid high price zones while maintaining process effectiveness so that the process is delivering what it's designed to do. Things like that I could imagine. There's probably a lot more to be done, which begs the question, or which justifies that such a project is looking at the introduction of artificial intelligence into the process design, or I should say systems design. And what is the outcome for the heat pump industry at large? Today we talked about heat pump recognition altogether, and I do think that we need a full recognition of the heat pumps by policymakers, and that means acknowledging that heat pumps are the best technology, being technology clear when it comes to the selection of technologies for future research programs, for example, understanding that heat pumps work well in industrial processes up to and hopefully soon beyond 200 degrees Celsius, understanding that heat pumps are an integrated technology that close energy cycles and can take waste heat from many sources. So if we look at the city context, and that was what we discussed this morning on the panel, then it would mean that we can avoid cooling units that are put on roofs or at the facades, because we can collect the waste heat from cooling into ambient thermal loops, and that serve then as energy source for heat pumps. But we also, if we deploy more heat pumps in cities, we avoid heat islands, we avoid pollution. And if you think the related costs to that, it is quite significant how many people die these days as the negative consequences of heat waves. There is this term of cooling poverty. People can't afford cooling. So if we deploy more heat pumps, we can make cooling available also to multifamily buildings, to social housing in a cost-effective way. And we avoid producing air pollution at the point of operation, which inevitably, independent of what you burn, will be the result of combustion technology. So for a city, the most modern way of heating is with a heat pump. And for an energy system, the most conducive technology to provide heating, cooling while balancing the electric grid is different combinations of heat pumps, thermal grids, and AI. That is my key takeaway. If everybody could take home that A heat pump investment is a no-brainer investment. And if policymakers could take home that your job is to create the framework conditions that for each and everybody of us, the decision in favor of a heat pump is not a cost and creates us a headache, but becomes an investment that will help us to live a better life and a more affordable and get more affordable energy supply, both for heating and cooling.